Okay, so today's lesson, topic 4 and 14, and what we're going to focus on here is first ionic versus covalent bonding, and then we're going to get into Lewis structures and shapes, and then hybridization with higher level later on, and formal charge and things like that. But I think I want to kind of focus first on the first section, kind of comparing ionic versus covalent bonding in a lot of different terms, and then going to Lewis structures. I figure kind of halfway, like a third of the way through the lesson, everyone that wants to be here will be here. And so then we can kind of cover the most ground with that, with Lewis structures. I'm going to show you the way that I do Lewis structures that works for all structures, whether they're expanded or suboptimal or octet. It all works for everything. So it's a very useful way to kind of do Lewis structures when you're having a tough time with them and you can't get the right structure. Okay, so the first thing we really want to kind of address is our ionic versus covalent. Okay, and a lot of different things we have to address when we're comparing these. Okay, the first is a definition. Okay, and for ionic, we talk about the electrostatic attraction between oppositely charged ions. Okay. Whereas with covalent, we talk about the electrostatic attraction between a shared pair of electrons and the positively charged nuclei. So first of all, you have to establish kind of the definitions of these two and compare them. It's a very popular multiple choice question where they ask, like, which one best defines ionic bonding or which one best defines covalent bonding. And so that's kind of a quick question, understanding what the attraction is. Okay. Now, we'll say the next one, qualitative identification. Okay. What I mean by that is, without using numbers and looking at a formula, how do you identify ionic versus covalent? So generally, ionic involves a metal and a non-metal, which includes polyatomic ions. So if you look at a formula and you see a metal or you see a polyatomic ion in there, you can immediately identify it as ionic. Whereas covalent is between two non-metals. So the easiest way to kind of look at these formulas is that. Feel free to ask questions on here too if there's anything that you need clarified or if you need me to slow down and things like that. Now, the quantitative way to do it is to distinguish between using electronegativity. And when you use the difference in electronegativity, you will find a different range for ionic versus covalent. Ionic, the difference when it's greater than 1.6 generally means an ionic bond, meaning that there is a transfer of electrons because the imbalance is so great that one atom essentially takes the electron from the other atom because there's such a difference in attraction. For covalent, you might get a difference between 0 to 0.4, which we call nonpolar covalent, and then 0.5 to 1.6 is polar covalent. Okay. And so that kind of tells you what kind of polarity the bond is going to have as well. Now, what you have to understand is this is kind of a spectrum. It's not a hard, like, kind of stop at 1.6. It kind of transitions through from 0 all the way past 1.6 to become more and more ionic as you go through. So like a 1.5 is, yes, technically classified as polar, but it's on the verge of ionic. And you will start seeing more ionic characteristics show up in those properties as you get higher in the polarity. So a 0.6 polarity versus a 1.6 polarity, there is a significant difference in how they behave with the kind of partial polarities and things like that. So do understand that the higher the difference, even within this an individual range, will matter. Naming, okay? Naming ionic compounds versus covalent compounds. With ionic compounds, it's generally metal and non-metal, but you convert this to IDE. You generally don't change the name of the metal when you're doing this. The only exception for this is when you have to put a Roman numeral for a multivalent metal. So if you have a metal, oftentimes a transition metal that has multiple oxidation numbers, you have to put a Roman numeral after the metal to identify it. So you might say something like iron 2 oxide. Okay. So that Roman numeral represents what the oxidation number of iron is, not the quantity of irons, the oxidation number of iron, so that you can form the right number of ions to make the formula. Whereas in covalent, you have to use prefixes, okay? So mono, di, tri, tetra, etc. Okay. Now, the first element, you leave the same. The second element, you change to IDE. In the first element, you don't use the word mono if there's only one. On the second element, you always have a prefix, regardless. Okay. So the best example I think of this is carbon monoxide. Because if I think of carbon monoxide and I think of that as CO, then that reminds me that I don't put mono on the first one, but I do put mono on the second one. And I always put a prefix on the second one. So it's kind of a good reminder of that for naming these structures. Remember, polyatomics also don't change names as well. They stay the same. Sulfate is always SO4, 2 minus. Questions so far? Properties, okay? General properties that we kind of address in comparing these. So these are mostly solid, okay? They have very high melting points and boiling points. They form a lattice structure of ions. They are only conductive in liquid, aqueous, or gas state because of the presence of free moving ions. So conductivity, based on the type of substance you're talking about, will have conductivity because of either free-moving ions in the form of ionic compounds or free-moving electrons in the case of metallic bonding, which we'll talk about a little bit later. For covalent molecules, state of matter varies. Okay, they generally have low to medium melting points and boiling points. Their intermolecular forces are broken down to LDFs, dipole dipole, and hydrogen bonding. And those IMFs dictate kind of the other physical properties like boiling point and melting point. And we'll talk about IMFs a little bit later on in this unit. Okay. I think those are the main things I wanted to kind of compare between these. So we'll stop there on the table. Okay. Metallic bonding, I'm going to kind of address down here kind of in its own. With metallic bonding, it is an electrostatic attraction. You kind of see a pattern here between delocalized electrons and a lattice of positive ions. Okay. Key thing here is you really want to kind of focus on the idea of the delocalized electrons. So every metal atom contributes its valence electrons to this delocalized kind of sea of electrons to give it its structure. So the electrons are kind of acting like the glue holding the lattice of the positive ions together. Okay. Now the strength of the metallic bond depends on the charge of the ions and the ionic radius. Okay. And if you want a greater strength, you want a higher charge and you want a smaller ionic radius. Now, the delocalized electrons allow for the conductivity in all states and malleability. Because unlike ionic compounds, they're not fixed ions. They are kind of a fluid of, not fluid, but they are ions that are surrounded by these delocalized electrons that are able to be moved. And so when you apply a force to it, essentially the layers of ions and electrons spread out away from the impact so that they're allowed to kind of change shape and flatten more and more and more. And so that's what gives it the kind of malleability and ductility that you have come to see with metals and their ability to be hammered into thin sheets and things like that. Another term that involves metallic bonding is an alloy, a mixture of, well, of a metal and another element or elements, okay? And so what this does is that when you mix your metallic bonding with other elements in there, it gives it enhanced properties or gives it different properties. And so without going into too much detail about this, but there's substitution alloys where a metal ion substitutes in the lattice. So something like bronze is an alloy of copper and tin, where the tin atoms kind of fill the lattice and displace some of the copper ions. So there's kind of this lattice of mixture of copper and tin atoms. And it gives it a much brighter luster and gives it some various properties in strength and durability. Brass, I believe, is copper and zinc. Things like that. The zinc is reinforcing the copper. The other type is called interstitial alloys. Okay. And that means usually what you do is you put a smaller element in the gaps of the lattice. So even when the positive metal ions are distributed about, there are small gaps in between them. And so you can fill those gaps to make things more rigid and harder, like, for example, steel, which is iron with carbon. So you infuse it with carbon to fill in the gaps between the iron ions to make it harder and stronger. Now, that does affect some of its malleability, obviously, because you're kind of restricting the movement of these ions. But overall, it is more rigid and sturdy and can withstand more force before it'll break. So those are kind of a couple of different couple examples of different alloys that you might need to be familiar with. Okay. Questions about any of that? Make sure it did. Okay. 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 Give y'all another second to write that down. Give me 1 second. Okay. All right. Let's talk Lewis structure. Okay. And this is the main thing I would say from this topic that shows up the most. Lewis structures, which leads to VSEPR, which leads to, again, in higher level hybridization and things like that. And we also have to do kind of resonance. So this is kind of the major idea behind this, especially in short answer. They like to ask about these structures and things like that. And so, okay. All right. Lewis structures. Okay. And Lewis structures show all electrons in a structure, okay? Whereas organic molecules only really show the bonding and the electrons that are necessary. They kind of leave out the lone pairs that don't actually involve anything. Lewis structures have to show all electrons in a structure. And so you will get docked points if you don't show the lone pairs on some of the terminal atoms and things like that. So this is why I think it's important to kind of reinforce that when you're drawing the structures. And so here's how I do Lewis structures, okay? There are two things that I do, okay? One, I calculate, I'm going to kind of dub these terms. I don't know, these aren't like technical chemistry terms, but I want to assign this. And so I'm going to call this the budget, okay? So this is the number of valence electrons available to use. So you're going to always want to calculate how many electrons you actually have to use, because your structure can only have that number of electrons. So it's really important. So for example, when you look at something like CO2, you see that carbon has 4 and oxygen has 6, and there's 2 of them. So that means you have 16 electrons, or if you divide by 2, you have 8 pairs of electrons to work with. And that's going to dictate your final structure. Your structure can only have 8 pairs because there's no other electrons for it to use. So budget's really important. Now, the second aspect that I do is what I call the test structure. Okay? The test structure, because with this, it feels like it's kind of guess and check, but what you do with the test structure is you draw the theoretically simplest possible structure. Okay. And that means, what that means is all single bonds. And that means any atom with 4 or more electrons receives an octet. Meaning that if something's only bonded once to something, then you give that atom 3 lone pairs. So it's a test structure. It's not supposed to make sense. It's like kind of the base structure you're working with. And then your job is to make that base structure meet the budget. So it's kind of like okay, here's the worst case scenario. Okay, I only have these many electron pairs. So then I have to change my test structure to make it fit the budget. And it works for all of them. And I'll show you where it really kind of comes into play with this as well. But so everything gets a single bonds. Any atom with 4 or more electrons receives an octet in here. So for example, CO2. Okay, I know what all know what CO2 looks like, but it's a good example to start with. I would draw CO2 like this, because carbon is going to be bonded to each oxygen individually, and everything needs to have an octet. Because oxygen has 6 valence electrons, carbon has 4, give everything an octet. When you count the number of pairs here, you have 10 pairs of electrons. Okay. The problem is your budget is only 8 pairs. So in reality, some of these lone pairs actually act as bonds instead, because there aren't enough electrons to afford every atom to have their own lone pairs. So the only way that they can be satisfied is if they share more pairs. And so if 10 minus 8 tells you need to have 2 more bonds, and you have to replace those lone pairs with 2 bonds, because every time you replace a lone pair on each, you can add a bond here. And every time you to get rid of these lone pairs, you can add a bond here, which then makes your structure this. And that checks out with your 8 pairs available. And I know with, even if you just drew the dots on each carbon and oxygen, that you could pair it up this way. But again, I'm here to try to simplify things so that way you don't have one way to do expanded octet, one way to do normal octet, one way to do suboctet, one way to do resonance. All that stuff, if you do this technique with Lewis structures, it will always work. And it will always get you the right structure. One way to do all of it. Okay. And even if you don't feel like you need the test structure, I think it's always important that you think about your number of pairs. Because even when you draw a structure that you think is right, double check the budget just to make sure you do it right. But I'm telling you this right now, this is the best way. It may feel longer for sometimes, but it's reliable, and you do it the same way every time. It takes less effort. Because in higher level, since we're already here, and this is only higher level, if you get something like SF4, okay? When you draw SF4 out here, S has 6, fluorine has 7, times 4. That's 34 electrons, or 17 pairs. Okay. The problem is when you draw your test structure, there's only 16 pairs. So you have an electron pair that's unaccounted for. And that extra electron pair goes on central atom. So then you just put it on the sulfur. Anytime you have extra pairs, you put it on the central atom, because that's an expanded octet. So that's how you figure out all your expanded octets as well. Okay. We're going to do a few of the exam problems here just to make sure, because this ties into some other things as well. Okay. Questions about that? This works for every single structure. Okay. Notice with the carbon dioxide, I had 2 bonds to give, and since both areas are identical, I distribute the bonds equally across. Okay. And in higher level, we'll talk about distribution of bonds a little bit more later on. We'll talk about, oops, sorry. Oh no. Hold on a second. I keep tripping this charger and it's messing up the left. Okay. Okay. So no questions about this so far. Okay. Okay. So here's an example of another one. This is back to SL. So we'll go back to SL here, because SL does need to know this.
This is correct, right?
For what?
NaOH.
So back to structures here. Okay. Here's where I think it gets really kind of helpful here, is that when you get into something like ozone. Okay. When you do this structure here, you do ozone. Okay, ozone is 6 electrons times, 3, divided by 2 gets you 9 pairs. Well, our test structure will have ozone looking like this. Okay. Now, here we have 10 pairs, but we know we need to have only 9 pairs in our budget. So what that means is we need to add 1 bond. Okay. In this situation, does it matter which bond we add that bond to? Doesn't matter.
No.
No, thank you, Alejandro. So what that tells us is because we have 2 places to add 1 bond, that this must be resonance. So doing the structure this way will tell you whether it's a resonance structure or not. Because if you have 1 bond that you have to put in more than 1 place and it doesn't matter which one is, then you'll have resonance. So what that tells you is that the structure of ozone is actually in one form this, and the other form this. That's what ozone is. So if you have a bond to add, but you have all the locations look identical and there's no differentiation, then you must have resonance, because it doesn't make sense to assign the bond to only one side, even when both sides are equal. So that's where resonance comes into play. And so this double bond is delocalized across both bonds. Okay. Which means effectively the bond order, which is essentially the relative bond strength, is there are 3 bonds per 2 links between oxygens. So effectively, the bond order is 1.5. So that oxygen-oxygen bond is effectively 1.5 oxygen bonds between each oxygen. Questions so far? Let me give you all a second to write this down. Yep. Okay. Let's do carbonate. This is another structure that comes up a lot in the IB discussion, is CO3 2-. Okay. Now, carbonate, carbon is 4, oxygen is 6 times 3. And since it's a -2 charge, you're going to add 2 electrons to that. So that's 24 divided by 2 is 12 pairs in your budget. So your final structure can only have 12 pairs. The problem is when you draw carbonate, it has 13 pairs. So what that tells you is you need to make 1 bond. And since all 3 locations are identical, you have resonance again. But in this case, you actually have 3 possibilities for where that resonance can occur. You can either have this, this, or this. So 3 possible different locations. And the IB will want you to draw these out if they say draw all possible resonance structures. They don't like the dotted lines. I think they're really confusing. And then sometimes kids get the wrong number of lone pairs on every dotted line and stuff like that on each auction when they draw dotted lines. So the IB will expect you to draw this. When they say draw all possible resonance structures, you need to draw yes, you'll have to draw all 3 with the carbonate having a 2- ion on each one. Okay. Questions about that? Okay. So what's the bond order of this structure here of carbonate?
(1.33).
How'd you get that, Alejandro?
It's 1 bond for 3.
Yeah, you could do it that way, or you just add up the total bonds divided by the links, right? So what Alejandro did is say, well, it's 1 divided by 3, so I just add that to 1, and that's effectively what it is. That's fine too. But yeah, it's a bond order of 1.33. So what that means is it's going to be in between somewhere between a single bond and a double bond, a little bit closer to a single bond, but still between those 2 values, that resonance. Questions? One of the resonance structures I think they don't explicitly say that you need to know. Well, they say on the syllabus that you need to know carbonate, benzene, and ozone, but not limited to that. One of the most common ones that's not limited, quote unquote, to that is Athanoate. Okay. Okay. Athanoate is CH3COO minus. Okay. And Athanoate looks like this. But notice how the auction, because there's no hydrogen on that second auction, those 2 auctions are identical. And so what ends up happening is there is resonance between those 2 auctions. So there is resonance between those 2 auctions in Athanoate, not ethanoic acid when there's an H bonded to the O, but when it's Athanoate, the ion, it actually resonates between those 2 linkages. And the bond order for that would be essentially 3/2, so 1.5. So it's going to be slightly stronger than the CO linkage in carbonate, but not that much stronger. Questions so far? Okay. But yeah, I would seriously look at doing Lewis structures this way to help you A, identify resonance, B, for higher level, identifying expanded octets, And C, just to simplify your Lewis structure drawing so that you don't have to think about it different ways. Again, minimize what you have to memorize. Even though it might feel like this is longer for some of these shorter, the simpler structures, it's more foolproof. And I think not having to think about which way to do it is going to save you time in the long run anyways. And again, I don't think you're going to be really pressed for time on these structures on the test. Okay. Okay. Having said all that, once you get the Lewis structure, because I'm going to tell you this right now, the IB doesn't do error carried forward on Lewis structures and shapes. So if you get the Lewis structure wrong, even if you identify the shape right, you're not going to get that mark because they treat those as independent. Even though that doesn't make sense to me, they treat those as independent answers and they are not connected to each other. And so you have to really kind of be careful about that here. So it's really important you get the Lewis structure right or you won't get the shape right and you'll lose both points. So be very careful about that. Okay. So VSEPR or VSPER, doesn't matter which way you say it, is called valence shell electron pair repulsion. Okay. And what that means is that atoms / electron pairs orient themselves to minimize repulsion. So these shapes that originated from all these Lewis structures are formed because these electron pairs are all negative and they have to try to orient themselves to minimize their repulsion so that they're as far away from each other as possible. And those shapes are derived from those concepts. And so what you need to remember for this is that a lone pair interaction is the strongest one. So two lone pairs, that means two full negative charges. So they're going to have the most repulsion. Then a lone pair versus a bonding pair is the next priority. And then last priority is bonding pair. So when you're trying to figure out what has the most impact on it, it's a lone pair with the lone pair first, and then the lone pair with the atoms that are bonded to the central atom. And then it's all the bonding pairs together.
Hey,
Hey,
John, how are
Hey,
you?
good. How are you?
Good. I'll be in 102 if anybody needs to spread out.
Okay, I appreciate it. Okay, so this is how the kind of shapes work. Now, I want to first talk about electron domain geometry. Electron domain or electronic geometry, okay? And there's a difference between electronic and molecular geometry. Now, electron domain / electronic geometry treats all electron pairs the same, meaning that it doesn't matter if it's a bond, it doesn't matter if it's a lone pair, they're all treated the same. They're all pairs, and we're looking at how they are shaped around the central atom, okay? So there are only 3 5 for higher level electronic geometries. Okay. So there are only 3 / 5 shapes that you need to know that are electronic geometries. And all the structures that fall under that domain have that structure. So there are the following. Linear, where you have 2 domains. Trigonal planar, where you have 3 domains. Tetrahedral, where you have 4 domains. Higher level, you have trigonal bipyramidal, which is 5 domains. And then octahedral, which is 6 domains. So if they ask you for the electron domain geometry or electronic geometry, these are your only 5 options, because the bonding pairs and the lone pairs are all treated the same, so it doesn't matter. Okay. So these are your only 5 or 3 electronic domains. So all you do is essentially you add up lone pairs and bonding regions, and that equals your domain. So bonding region means it can be a single bond, a double bond, or a triple bond. That's all equal to 1 region. So it doesn't matter how many bonds are. Oh, that looks really weird. Okay. Is 1 region. So a single, double, triple bond is 1 region in all accounts and purposes. Good. So if you have water, for example, water would have 4 domains on the oxygen. You'd have 1, 2, 3, 4. 4 domains. Ammonia would still have 4 domains. 1, 2, 3, 4. Okay. So they both technically have the same electronic geometry, as tetrahedral. Now, molecular geometry, that's a different story, but both of those are the same here. CO2 would have 2 domains. And we're only talking about the central atom here, so that's 1 domain, 2 domains. So that would be linear. Okay. Questions about that? Now, I drew these shapes. You're probably wondering why I drew these lines up here, not just to illustrate, but I actually drew them in a certain way to help you with molecular geometries, because I think visually, I think sometimes people struggle seeing the shapes. And so I drew them in a particular way here that I've always drawn them to help my students remember what the molecular geometries are. And so molecular geometry is the shape formed by the arrangement of atoms. Okay, so lone pairs are affecting the shape, but we don't identify it as part of the shape. So they affect the shape, but we don't identify it as part of the shape. Now, if you have no lone pairs and all you have is bonds, then it doesn't matter. Your electronic geometry is the same as your molecular geometry. You'll have linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And you will have the angles that are according to that. 180 degrees, 120 degrees, 109.5 degrees, 90 and 120 degrees, and 90 degrees. Let me change the color here just to make sure that we differentiate that these are higher level. Now, linear, you can't have any, linear, you can't really have any different shapes, but trigonal planar, if you replace one of those lines with a lone pair, you would remove that line from the shape. And so what I would do is take that line and remove one. Like I would cover it up with my hand if I was drawing this on paper, because this would now be a lone pair. Okay. But what's the shape that's remaining of the lines that is present there? Does anyone remember what that shape is called?
Bent.
Bent. It literally is a bent line. And it's about 117 degrees. So every time a lone pair impacts it, it usually affects it about 3 degrees. Okay. In a tetrahedral, we take away this first one. And remember, you have to think of this in 3 dimensions. What shape is left of what I've highlighted here? So think of 3 legs here. What shape is that?
Pyramidal.
Pyramidal. And that angle will be about 107 degrees. Okay. Now, if we take away this first one and make that a lone pair, we're going to take away another one and make it a lone pair. Now, they're all the same away from each other, so we're just going to take this one away here. Actually, you know what? Maybe not that one. Yeah. Yeah, just leave it on the table. Okay. I'm going to take away this one. You're welcome. So now I've got 2 lone pairs and then this. Okay. What's my shape there? I can't see hands raised, by the way, so you just speak up. Sorry.
Is that the seesaw?
No. Look at what it looks like compared to another shape here.
Bent.
It's also bent. Seesaw goes in a higher level, and you'll see that in a little bit more later. So bent, but this bent is about 104.5 degrees. Yeah, sorry, I forgot. I should have told you I can't see cameras because I'm trying to make the screen as big as I can, so I can't see you raising hands like I do in class. So you just unmute yourself and you can say it. So apologies. I hope no one was like raising their hands and wondering why I'm not calling on them. Okay. So that is the extent of your SL. So if you remember these 3 shapes, these line shapes, and you just cover up lines as necessary, you can generate all 6 shapes with only 3 shapes memorized. Again, minimizing what you have to memorize. Okay. Now, higher level, because we're already here, I'm going to talk about it here. Okay. Which of these lines is the furthest away from all the other lines that I've drawn here? Which of these lines is the furthest away from all the other lines?
The one going straight up.
The one going straight up. Thank you, Peter. Okay. So we're going to erase that one. And we're going to make a lone pair here. Okay. Think of this in 3 dimensions. So what shape is this, Moritz? Moritz, what shape is this?
Seesaw?
Yeah, this is a seesaw. Do you see how it forms the two base legs and then like the flat plane over there? That's your seesaw. You don't need to know angles for this, so don't worry about that too much. Now, if you made a lone pair that was up here, which line is the furthest away from that lone pair so that you can minimize repulsion? Which line is the furthest away from that lone pair?
Bottom left or right?
Bottom left or right. So guess what? We erase one of those and we make it a lone pair. What shape is left? Don't overthink it.
Is it T-shaped?
It's T-shaped. Exactly. Okay. And then we take that idea again. Now, you have two lone pairs here. Which lone pair is the furthest away from both lone pairs in this scenario? I guess maybe it's kind of hard to see. But wait, what'd you say, Alejandro?
Bottom left.
Bottom left. So guess what? We take away that. So what's left?
Linear.
Linear. So guess what? You've turned one shape into four. Because all you've done is cover up a line each time and you create every single shape. Okay. Okay. Doesn't matter which one I take away from the octahedral one. Does it matter?
No.
No, because they're all 90 degrees. So I'm just going to take away the top one for simplicity's sake. Okay. Okay. Remember, this is in 3 dimensions. What kind of shape is formed here?
Square pyramidal.
Square pyramidal. Okay. Now, which next line is going to be the one to go after the first lone pair? Which one needs to go away from that? Which one's the furthest away from that lone pair?
The bottom one.
Thank you, Alejandro. Yeah, Alejandro's carrying it right now. Okay. So what shape's left?
Square planar?
Square planar. Thank you, Moritz. There you go. Square planar. Because the lone pairs are on opposite sides, they repel equally, so everything flattens back out. Okay. Now at this point, does it matter which one I take away next? No, it doesn't.
No.
So I'm going to take away this one here. So what shape do we have left now?
T-shape.
T-shaped. Okay. And then we take the last one, which is the furthest away from that. And it's what?
Linear.
Linear. Exactly. So look, you've just diagrammed every single molecular geometry you need to know, including the 5 electron geometries. And to be honest with you, the way I tell my students is, if you know these 5 shapes here, you will know every other shape. And for higher level, it's especially helpful because think about it. What would you rather memorize? Okay. Would you rather memorize 9, 12, 15 shapes? Or would you rather memorize 5 shapes and then figure it out when necessary? I think the 5 shapes is much easier. And if you draw it like this, you just cover up with your fingers or erase them as you need, and you'll see what shape is left. It takes a little bit of practice, but I think it's going to be a lot easier for you to do that than having to memorize 15 shapes. Maybe with SL, 3 versus 6 is not a huge deal, but 5 versus 15, I think is a huge deal here. And that's kind of the trick that I tell my students about how to remember these shapes. Okay. So yeah, let me make a note that this is higher level for those of you looking back at the notes later on. I think that's really useful. Questions about that? Now, remember, the reason why it's linear at the bottom part for higher level is because the lone pairs all cancel each other out. Their vectors kind of cancel each other out. So that way, everything else is just a line. Whereas in standard level, when you have a lone pair, there's an unbalance there, which causes everything else to bend away from it. Hence why you get a pyramid or why you get bent shapes with the trigonal planar bent and the tetrahedral bent. But you just have more bending because you have 2 lone pairs there instead of 1. But they don't cancel each other out because in 3 dimensions, they're not in a 90 degree angle. They're at 109. And so they don't cancel each other out. Questions about that? It's a lot to take in, but it's a good review. Okay. Now, what we haven't talked about yet is giant. Oh, sorry. Let me scroll back. Let me zoom back in. Giant network covalent. Okay. Giant network covalent structures are structures that are all covalently bonded, but they're not independent molecules like water or like CO2 and stuff like that. They're just a whole network, and you can't really break it up into independent molecules. And so there are 5 technically, 4 major carbon ones, and then there's silicon dioxide as well. Okay, and so the allotropes of carbon we care about. Okay, allotropes, first of all, are molecular forms of elements. Okay, so an allotrope is any molecule that's derived of only one element. Okay, so we have 3 major ones here. We have graphite, diamond, and fullerenes. Okay, I've not planned out this table yet, so we're about to see how this works out. Okay, so graphite are sheets of carbon that form hexagons. Okay, and so the carbons are bonded such that they form hexagon shapes, which means that they are trigonal planar in shape. Okay, because each carbon is only bonded to 3 other carbons. Okay, and there's a delocalized electron from each carbon kind of moving around, which causes the attraction between the 2 sheets, between the multiple sheets of graphite. Okay, and it is conductive. Okay, diamond. Actually, you know what? One more thing before this. Okay, I forgot. I should say this as well. 1 sheet of graphite equals what we call graphene. Okay, so graphene is one layer of graphite, just one single layer. And it was actually determined by a scientist that the easiest way to remove a layer of graphite off of something was just Scotch tape, because the attractiveness of Scotch tape was so specific that you could actually peel layers of graphene off of carbon with just Scotch tape. I think he won a Nobel Prize for that, which is pretty impressive. Okay. I think I'm going to try to win one with just a stapler. We'll see how that works. Okay. Tough crowd today. They're all on mute, and so it's okay. Diamond is tetrahedral in shape, and each carbon is bonded to 4 other carbons. So there is no delocalized electrons here, and so it is non-conductive and the hardest natural substance. So diamond is tetrahedral, carbon bonded to 4 other carbons. Fullerenes or Buckminster fullerenes. These are your kind of C60 structures, where you have 60 carbons in kind of a spherical shape. So the carbons bonded to 3 other carbons. Okay. But because they are kind of in an independent kind of giant sphere, they tend to be not conductive, because the electrons can't really move between the different fullerenes. Okay, and it's 12 12 pentagons and 20 hexagons. Okay. You can't just say soccer ball shape, even though it is kind of essentially a soccer ball, but you do, if you're going to say soccer ball, you still have to state how many pentagons and hexagons are there. If you want to use the actual term is truncated icosahedron, but I don't expect you to memorize that. So I would just go with the 12 pentagons and 20 hexagons. And it looks like I do have pictures of each of these that way you'll be able to kind of see it better. Where is it? Yeah. Okay. Here you see the different allotropes of carbon in their kind of standard state. And so you can see the graphite with the graphene layers that are stacked on top of each other form the hexagons. Each carbon is only bonded to 3 other carbons. In the bottom left, you see the fullerenes, which are those 20 hexagons with the 12 pentagons holding it all together, making it into a sphere. Diamond on the right with tetrahedral bonded to 4 other carbons. And then carbon nanotube is essentially a fullerene, but expanded and just lengthened with additional carbons, making hexagons and hexagons and hexagons. And then at the end of the nanotubes, if they want to enclose them, then they would use pentagons to enclose the ends of the carbon nanotubes. Questions about that? Okay. SiO2, silicon dioxide. You would think that silicon dioxide, because it's in the same group as carbon dioxide, that it would have a similar structure as carbon dioxide. But it turns out because silicon is slightly larger, it doesn't really have the ability to form that kind of independent structure. So what happens is that it forms a network covalent solid where there's an Si bonded to 4 oxygens like this, kind of in a network. And I'll show you a better picture of it. It looks like this, okay? But if each silicon is bonded to 4 oxygens, why is it called SiO2? Why do we think it's called SiO2? If each silicon is bonded to 4 oxygens, why is it not SiO4?
Because when you boil it, it becomes SiO2.
No, look at each of the oxygens, okay? The oxygens are the ones in brown, okay? How many silicons are each oxygen bonded to?
2.
2. So in other words, it's not that each Si is bonded to 4 O's, it's 4 O's are bonded to 2 Si's. Because if you look at, like for example here, this oxygen, this oxygen, this oxygen, this oxygen, yes, they are all bonded to silicon, but they're also bonded to an additional silicon in each direction. So really, each oxygen is doing double duty. So that's why it's SiO2, because it's really Si2O4 when it's bonded to each of these oxygens, and so it reduces down to SiO2. So the number of silicons and oxygens is 1:2 ratio in the entire structure. And it does form a tetrahedral structure, much like diamond. That's why it is very hard. And we know this commonly as quartz. And that's kind of what makes up a lot of minerals and stuff like that. Not as hard as diamond, but fairly difficult to break. So common question that the multiple choice I've seen it ask a lot is they'll ask you to compare the bonding in CO2 versus SiO2. And if a student hasn't studied SiO2, they might assume that it bonds the same way as CO2, and they would say that. But you have to know that CO2 has 2 double bonds with oxygen, and Si has 4 single bonds with oxygens in a network covalent. So that difference is really important, and that shows up in multiple choice questions a lot, making sure, holding you accountable for understanding the shapes and things like that.
Mr. Chong,
Yes.
could you almost think of SiO2 as like the repeating species or whatever, like what we're doing in OChem?
Yes, if you want, yeah, you could kind of imagine it as like a repeating unit in the entire thing. Yes, where, yeah, really it's just SiO2 repeating over and over and over again in a tetrahedral structure instead of SiO4, because each Si really only has ownership of 2 oxygens. Yeah, it's an interesting way to think about it. I hadn't thought about it that way, but yeah, you could treat it like Moritz said. If you look at it and you treat this as your repeating unit, then this is your repeating unit, and then this is your repeating unit, and this is your repeating unit, and this is your repeating unit. Notice that how SiO2 accounts for every single atom in the structure without overlapping. So that's a good point, Moritz. I like that idea. Okay. I forgot one thing about bonding that I want to talk about here. And so this kind of goes back, this is out of order, but I saw this on the syllabus tracker guide, and it's some reason it's way down there, and I don't know why. But another reason why Lewis structure, the way I do it, is really convenient is when you have coordinate covalent bonds. Okay. because coordinate covalent bonds are not not obvious when you're drawing Lewis structures by pairing up electrons, because coordinate covalent bonds occur when one atom donates both electrons to a bond. Okay. And so in these cases, one atom has an additional pair of electrons that it can donate to another atom to complete both their octets. Okay. And the best example that I can think of here is carbon monoxide. Okay. Now, carbon monoxide's 4 plus 6 is 10 divided by 2 is 5. So when you draw carbon monoxide out test structure-wise, you get this, which is 7 pairs. So what that tells you is 7 versus 5, you need to have 2 more bonds. So it ends up being this. The problem is, though, if you just drew out your electrons, you wouldn't ever see this structure here, because carbon only has 4 electrons. And so how are you going to get a triple bond and a lone pair on there? It's because this last bond, we draw an arrow to show that it is a coordinate covalent bond. And that's another reason why I like doing it the way I showed you, is because it will take out the concern about coordinate covalent bonds, because that's the only way the structure will work. And so it takes the guesswork out of this. So generally you draw an arrow pointing in the direction in which the coordinate covalent bond is going. So oxygen's donating 2 of its electrons to the carbon, and that's why the arrow is pointing toward the carbon. If you're wanting a kind of a quick and easy way to figure out whether a structure has coordinate covalent bond or not, most atoms have a desired number of electrons a number of bonds it wants to have. For example, like oxygen wants 2 bonds and nitrogen wants 3 bonds, because oxygen has 6 valence electrons and nitrogen has 3 valence electrons. So anytime the number doesn't match 2 or 3, you're going to have a coordinate covalent bond. Like, for example, NH4 plus, because NH4 plus looks like this. And what it turns out is that nitrogen actually has to donate its pair of electrons to one of the hydrogens to form the structure. And so that's a coordinate covalent bond. H3O plus is the same way. The only way that it can occur is if the oxygen donated one of its pair of electrons to one of the protons to make that. So anytime you see oxygen or nitrogen having a weird number of bonds where it has like 3 bonds when it's supposed to have 2, or 4 bonds when it's supposed to have 3, then that is usually an indicator of a coordinate covalent bond. Oh, excuse me. Questions? I think we have about 15 more minutes of SL, where we talk about IMFs, and then we'll take a break, like about a 5 or 10 minute break, so that HL can kind of stretch, and then we'll finish HL after that. I don't know how long the H is going to take, but hopefully it's not too long. Okay. IMFs, or intermolecular forces. Okay. And for us, this is having to do with covalent molecules. Okay. And so therefore, this has to do with molecular polarity. Okay. And so this does factor in bond polarity, but you want an overall difference of polarity to form a polar molecule. And so there are 3 degrees of IMFs for covalent molecules. The first one is London dispersion forces. Okay. LDFs for short. Now, these are the weakest IMF, but they're present in all molecules. Okay. And so, but they are the strongest IMF in nonpolar molecules. So in nonpolar molecules, they are the strongest. And identifying a nonpolar molecule really has to do with identifying your bond polarity. Okay. And so what you'll see is looking at the bond polarities overall and see if there's a net difference in polarity. And so, for example, something like CF4, even though each bond is polar, the fact that they're pulling in equal and opposite directions for polarity, it cancels each other out because around the outside of the molecule, there is no difference in polarity. They're all the same negative. So there's no overall polarity for the molecule. So this would be a nonpolar molecule with polar bonds. Okay. And so when you have a molecule that is nonpolar, meaning that there's really no region of polarity in it, what happens is you get what are called temporary dipole moments, where the electrons are constantly in motion around all the bonds, and occasionally they are moving such that one fluorine in this example becomes slightly less polar. And that makes the molecule have a temporary polarity, which then causes a chain reaction. Which generates this weak attractive force between these kind of random polarities that are occurring between all these molecules. So keep in mind temporary dipole moments. And also, the strength of this increases based on mass. So your LDFs increase in strength as mass increases. I think the best example of that is thinking about fluorine gas going to chlorine gas, going to bromine liquid, and going to I2 solid. Okay. As the increase in mass, the attractive forces are strong enough to actually change states of matter. And so I2 being the greatest mass is in a solid state because the attraction forces are strong enough to form that. Okay. Questions?
Temporary dipole moments are considered different from LDF, right?
No. Temporary dipole moments are LDS, Alejandro.
Thank you.
Yeah. Sorry, I shouldn't have maybe color changed here. This should still all be gray. I was trying to like make it kind of a point, but it's still all LDFs. Sorry. Once the molecule has actual polarity, we get into what's called dipole dipole, which literally means two poles and two poles. And so this occurs in polar molecules, where there is a difference in polarity in the molecule, and you see that. And this polarity means permanent dipole. These have a permanent dipole moment. So each of these molecules have some polarity. So like, for example, HCl has a always positive and always negative end. And that means that they will attract the always positive and the always negative end of an adjacent molecule. And so these are permanent, so they don't switch on and off, so they're always there. So that's why this is stronger than LDFs, because the dipole moment's always there. So there's always a forced attraction between the molecules. And there's a unique version of dipole dipole, which is very, very strong. And that's called hydrogen bonding. And so this is a type of dipole dipole. But in this type of dipole dipole, the difference of polarity is so strong, it's as if there's a bond forming, because when you have H bonded to N, O, or F, these are the three most electronegative species that are the smallest atoms on the entire periodic table. And so this creates a huge positive and a huge negative in the structure, which means that when they come into contact with another molecule, this attraction between the species here, sorry, that looks like Ni, but that's really N with a lone pair. This attraction is a hydrogen bond. And so they call it bond because it's closer to kind of a covalent bond than a dipole dipole, because it's such a strong attraction, because there's such a strong positive and negative charge there. It's a very strong attraction. Don't mix that up with this, which is just a covalent bond. Okay. And the IB has in the past asked you to diagram a hydrogen bond and show where it is and compare it to a covalent bond. So don't make that mistake. Covalent bonds within a molecule, a hydrogen bond is across two molecules. And it has to be H bonded to NO or F. It can't just be a formula that has NO or F and H. It has to be bonded with the NO or F. And like they'll like to try to trip you, and they'll say like something like this, or like they won't write it out. They won't write the bonds. They'll just write something like this. And then students will see, oh, there's an H and an O, so it must be hydrogen bonding. But in reality, none of the hydrogens here are bonded to the oxygen. So you wouldn't consider that hydrogen bonding. Okay. And you've got to remember that when we're boiling or melting and stuff like that, all you always are doing is breaking IMFs. You're never breaking bonds in your structures. Don't ever say the word bond unless it's prefaced by hydrogen bonds, okay? Because when you start saying bonds, you're implying that the structure is actually breaking down and the bonds are breaking, and you're separating the atoms in a molecule. You're not. You're separating the molecules apart from each other because you've given them enough energy to stray apart. You never break bonds. IMFs determine all your physical properties and things like that. Your bonds determine your chemical properties. Okay. One last thing. Okay. Your LDF and your dipole dipole are what we call van der Waals forces. Let me clean that up a little bit. Van der Waals forces used to be interchangeably used with London dispersion forces, but it's been corrected now that van der Waals forces encapsulate both dipole dipole and London dispersion forces. So you can't use van der Waals forces to describe nonpolar interactions because it actually incorporates both polar and nonpolar interactions. So be careful about that in old exams and stuff like that that you look at. You might have an issue with that because sometimes the question is worded weirdly. But London dispersion forces are one type of force. Van der Waals encapsulates both types of those forces. Okay. Questions about that?
Where would induced dipole dipole be?
Yeah. Induced dipole dipole. See, here's the thing with that, Alejandro. What I'm talking about here with these three is when in pure substances we're talking about this. So like in London dispersion forces, it's just pure CF4. Induced dipole dipole kind of fits in between these two, but it happens only in mixtures. Because an induced dipole dipole is when a dipole molecule, a polar molecule, gets close to a nonpolar molecule and induces a polarity to it, which then causes a weak attraction between them. Does that make sense, Alejandro?
Yeah.
So it happens in mixtures when you have dipole-dipole molecules with London dispersion forces molecules, and the polarity often affects the nonpolar molecule and induces a dipole in it so that they can attract. Now, this doesn't always work because sometimes like the attraction within like the reason why water and oil don't mix with each other is because the difference in attraction is so much that water would just rather attract itself than try to induce a dipole in oil. That kind of happens more with like kind of weak dipole structures and things like that versus London dispersion forces. And so it induces a dipole with the adjacent structure. Okay. Questions? Other questions? Okay. All right. Let's take a 9-minute break. We'll resume at 11 a.m. for higher level. SL, you are done. Higher level, what we'll talk about in our section is sigma and pi bonding, formal charge, expanded octet, and maybe some, well, hybridization for sure, and then maybe some ozone depletion, or I might save that for later in actual class because I don't think y'all have kind of gone over that. So I may say that for actual class instead of this review session. Okay. All right. I will see y'all in 8 minutes. Okay. So now that the break is over, what we're going to talk about are 3 things for higher level. I'm going to save ozone for later. So that's not going to be in this video, but we're going to talk about formal charge. We'll talk about sigma and pi bonds. And then we will talk about hybridization. Hybridization. And kind of encapsulate these 2 things kind of go together. Okay. So, okay. Formal charge. Okay. Formal charge, okay, is used to deduce the preferred Lewis structure when multiple possibilities exist. Okay. Now, it is essentially what charge an atom would have if all electrons were equally shared. Meaning that had the same electronegativity, and therefore, essentially what you want to think about is every time you're bonded with between two atoms, each atom would get one of those electrons, because when you have equally sharing, then each of them have ownership of one of those electrons. Okay. Now, the formula that I do for this is this: valence electrons minus bonds minus lone electrons. And just a reminder, lone pair equals 2 lone electrons. Okay. Now, sometimes the IB will do like valence electrons minus bonding electrons divided by 2 minus lone electrons. It doesn't matter. Like, I just say number of bonds, because every bond represents 1 electron for each atom, because each bond is going to break evenly. Okay. Now, when you look at a structure that has a possible difference in Lewis structure, let's say, for example, SCN minus 1. SCN could look like this. And it looked like all 3 of these ways it could exist, because technically these all match the required electrons for each atom. Technically, they all have an octet and everything is balanced, but one of these structures is better than the other 2. Okay. And so what we'll do is we'll solve for the formal charge for each of these. So for S, and then C, and then N. Okay. S, in this case, normally has 6 valence electrons, and you have 1 bond, and you have 6 lone electrons, so that's a -1 here. Here, it's 6 minus 2 minus 4, that's 0. Here, it's 6 minus 3 minus 2, that's +1. Carbon has 4 valence electrons normally, and has 4 bonds in all of these with no lone electrons, so it always has a 0 formal charge in each of these structures. N has 5 valence electrons. On the first one, it's -3 minus 2 is 0. The second one, it's -2 minus 4 is -1. And here it's 5 minus 1 minus 6 is -2. Okay. Now, choosing the right structure entails 2 things. You want 1, FC values closest to 0. So you want the formal charge to be as close to 0 as possible. So that rules out this structure here. Okay. Now, the only difference between these 2 structures on the left and the center are where the charge lays for the overall molecule. And that's your tiebreaker. Okay, let me write it out. Your tiebreaker is the negative charge is on the most electronegative atom. Okay, so if you have a tiebreaker here, let me pull up my electronegativity. I don't think S and C are the same. That's gonna be awkward if they are, but I don't think they should be. Yeah, okay, S is a little bit less. Okay, good. Whew. So here, the negative charge goes on the most electronegative. N is 3.0, S is 2.5. So the N should get the charge, so therefore this is the preferred structure of SCN minus 1. And yes, I have seen on the IB exam where they just have a table and say calculate all the formal charges of the atoms in each structure. And it's like a 6-mark question. So it is important that you know how to do this for a higher level. Questions about this? Okay. Sigma bonds and pi bonds. Okay. Okay. Covalent bonding occurs when there is an overlap of orbitals. Okay. And there's 2 types of overlaps that you might have. The first one is called a sigma bond. Okay. It is the first bond between 2 atoms. So no matter what, if you have a bond between 2 atoms, the first one is always a sigma bond. Wait, Emily, did you say you were going to try to use the O2 probe? Because I didn't make your solution because I thought you said you were going to try the O2 probe. Yeah. The O2 probes, oh, sorry, give me 1 second. So sigma bond is the first bond between 2 atoms. Okay. And it is the axial overlap, also known as kind of a head-on overlap. Bless you. directly between, handwriting's getting worse and worse, between two nuclei. So that first overlap between two nuclei that's your sigma bond. Okay, so it's between the two nuclei, and that's your first bond that occurs here. Now, because there's only room for one bond there, because you can only overlap once in that space, this introduces what's called a pi bond for additional bonding. And since you can't take up the space that's in between the two nuclei, this is caused from a parallel overlap of unhybridized p orbitals. Okay. And so here the density occurs above and below the plane. So here what you would imagine is a p orbital, and that, maybe I'll highlight it instead. That density of the electrons jumping between the p orbitals creates that bond that's attracting. So there's an electron density that's above and below the sigma bond that creates one bond. This is one pi bond, by the way. Even though it's two regions, it's still one bond. Okay. So know the difference between a sigma and a pi bond. And so remember, these are the additional bonds. And so if you have a double bond, that means there's one sigma bond and one pi bond present in there, because there's always a sigma bond, and then every other bond after the first bond is a pi bond. So a triple bond would be one sigma bond and two pi bonds between every linkage between an atom. So for example, if you have CO2, you would have two sigma bonds and two pi bonds. One sigma bond between the first left O and C, and the one sigma bond between the right O and C. And then the two additional bonds that are there are pi. And you can kind of see, I have a good diagram of what CO2 looks like when you actually have your orbitals kind of linked together. It looks like this. So notice, let me just move this. Notice there's a sigma bond in between the two carbons, and then there is a pi bond, and the pi bonds have to be in different planes on each oxygen because they can't overlap, right? So one of the pi bonds is vertically kind of the y-axis, and the other pi bond is in the z-axis. That's kind of coming out towards you here. And so that is what kind of those bonds look like when you're forming sigma and pi bonds. Okay. Questions on that? Clarifications? I think what I'll do is I will probably, when I upload the YouTube video of this lesson, I will probably put a link in the comments to these Schoology notes. To these Notability notes, so that if you want to download them and follow along, then you can. Okay. Hybridization. Okay. Hybridization is a tricky thing because it helps explain quite a bit about bonding and stuff like that, but it's still very kind of abstract. And so the idea is this, okay? The problem with carbon is that when you look at carbon, it's 1s2, 2s2, 2p2. And these are atomic orbitals. 1s orbital and 3p orbitals. Okay, actually, let me just write p there so it's not confusing. The problem is we know carbon bonds 4 times. And the way carbon is atomically arranged, it doesn't make sense. And the problem is these have different energies. 2s has a much lower energy than 2p. So it doesn't make sense for an electron to jump up into the 2p to evenly distribute because it takes more energy. So what scientists had to come up with is they realized that what happens is that those 4 orbitals all hybridize into an amalgamation of all 4 orbitals into 4 equal orbitals of equal energy. That way, when the electrons were bonding or distributed, they could be distributed equally. And so this created 4 equal energy orbitals. And these are called hybrid orbitals. Okay. And experimentally, that's proven because all the bond lengths are the same. And let's see, the bond lengths are the same and the angles are the same. Because if you had p orbitals bonding, they'd be 90 degrees from each other. And s orbital would be a whole different issue. But it turns out that when you have carbon bonding like in CH4, they all end up being bonded at the same angle. So what that tells you is that you can't use s and p orbitals. You have to use a hybrid orbitals to do that. And it looks kind of like this for a little bit better drawing here of hybridization. It looks like this. So you take 1s orbital, 3p orbitals, make 4 identical hybrid orbitals. And that's what we were trying to draw here. And they're known as sp3 orbitals because they require 1s and 3p's to generate 4 equal orbitals. So each orbital has a little bit of the s orbital in it and a little bit of the p orbital in it, and they distribute in a tetrahedral shape here. Okay. Questions? So when do you need hybrid orbitals? Okay, you'll need hybrid orbitals for sigma bonds and lone pairs. So every time you look at an atom, the number of sigma bonds it has and number of lone pairs it has tells you how many hybrid orbitals you have, which then tells you the hybridization. For example, CH4 has 4 sigma bonds on the carbon, no lone pairs. So that means you need 4 hybrid orbitals. So that means you need to take the s orbital and the 3p orbitals, hence a hybridization of sp3. So for example, CO2, very common example again, has 2 sigma bonds and 0 lone pairs on the carbon. So therefore you would need 2 hybrid orbitals. Okay, 2 hybrid orbitals. Okay. Now, if you need 2 hybrid orbitals, that means you'll need an s orbital and 1 p orbital. So the hybridization is sp1. So really, it's just a matter of figuring out A, how many hybrid orbitals you have, and then B, therefore translating that into how many atomic orbitals you need to use. And you start with the s and you keep adding on p's until you get to the right number of hybrid orbitals. But let's say this. Let's say you needed 5 hybrid orbitals. Let's say you needed 5 sigma bonds on a structure. What's your problem here with 5 hybrid orbitals? What's your issue with this? What's your problem?
You have 1s and 3p orbitals.
That's all you have, right, Alejandro? So you're limited based on your s and p orbitals to only 4 hybrid orbitals. So to have an expanded octet, what orbital do you need to include into this hybridization? What type of orbital?
D.
D. So this is why expanded octets require an empty d sublevel, because the empty d sublevel allows them to contribute d orbitals into hybridization, and so you get sp3d1 or dsp3, depending on how you want to write it. It doesn't matter. But either way, you get a hybridization due to that. So that's why, like, whenever you look at what atoms can have a expanded octet, you say, okay, does it have 5 or more valence electrons? And does it have an empty d sublevel? That means, is it on period 3 or greater? And if it does, then there's always an empty d sublevel, so you can do hybridization for it. And so really the maximum you'll have is S, P, P, and then D, D, which is 6, which is sp3d2. So that would be the highest hybridization that you'd have to do. Questions on that before we kind of wrap up? Because there's one more thing I want to talk about, like a little bit tying back to shapes and stuff like that, because you do need to see it. But questions about what this I've written so far? Okay. So it turns out that essentially hybrid orbitals are essentially the equivalent of electron domains. So you can tie the number of hybrid orbitals with the electron domains. So if you have sp1, that means you have 2 electron domains, which therefore means it is linear. sp2 is 3 domains, so it's trigonal planar. sp3 is 4, it's tetrahedral. sp3d1 is 5, that's trigonal bipyramidal. And then sp3d2 is 6, so that's octahedral. So the hybridization does tell you what kind of shape of electron geometry it will make as well. So this is electronic geometry. So be able to relate the shapes with electronic geometries. Now, be careful about what kind of hybrid orbitals you have, because if you have lone pairs, that affects your molecular geometry, which then you'll have to kind of progress like we did before in the SL section of the lesson, where we start changing the electronic geometry into molecular geometries. But if you are just if it asks you, what kind of shape has an sp3d1 hybridization, you say, well, that has 5 electron domains, so therefore the geometry, electron geometry, must be trigonal bipyramidal for electronic, at least.